What if I told you that the very act of looking at something changes what it is? Not metaphorically, not philosophically, but physically and measurably. There exists an experiment so simple that you could set it up on your kitchen table, yet so profound that it has haunted physicists for over a century. It has been called the most beautiful experiment in physics. It has also been called the most disturbing. This is the double slit experiment, and by the end of this video, you will understand why Nobel laureate Richard Feynman said it contains the only mystery of quantum mechanics. Welcome to the Conscious Observer. I am your guide into the deepest questions about reality, consciousness, and the strange universe we inhabit. Today, we shatter everything you thought you knew about how the world works. Imagine a wall with two narrow vertical slits cut into it. Behind this wall is a screen that can detect where particles land. Now, imagine firing tiny particles, let us say electrons, one at a time toward this wall. Each electron must pass through one slit or the other. Simple enough. You would expect to see two bands of impacts on the detector screen, one behind each slit, like throwing tennis balls through two doorways. This is exactly what our everyday intuition predicts. After all, a particle is a thing, a tiny bullet traveling through space. It has a definite position. It goes through one door or the other. But when we actually perform this experiment, something impossible happens. Instead of two bands, we see many bands. A pattern of alternating light and dark stripes appears on the screen. This is called an interference pattern, and it should not exist. Interference patterns are the signature of waves, not particles. Think of dropping two stones into a still pond. The ripples spread outward, and where they meet, something interesting happens. Where two peaks align, they create a bigger peak. Where a peak meets a trough, they cancel out. This creates a complex pattern of reinforcement and cancellation. This is exactly what we see on our detector screen with electrons. But here's the problem. We are sending electrons one at a time. A single electron leaves the source. A single electron hits the screen. There is nothing for it to interfere with. Yet somehow, over thousands of individual electrons, each one arriving alone, the interference pattern emerges. It is as if each electron interferes with itself, as if each single particle somehow travels through both slits simultaneously and meets itself on the other side. The founders of quantum mechanics proposed a radical solution. They said the electron is not really a particle until we detect it. Before measurement, it exists as a wave of probability, a mathematical ghost spread across all possible paths. This wave function, as they called it, passes through both slits at once, interferes with itself, and only when it hits the detector does it collapse into a single definite point. Niels Bohr and Werner Heisenberg championed this view, known as the Copenhagen interpretation. The electron has no definite position until observed. Asking where it was before measurement is meaningless, like asking what is north of the North Pole. This was not a statement of ignorance. They were not saying we simply do not know which slit it went through. They were saying the question itself has no answer. The electron went through both, and neither. Reality, at its most fundamental level, is not definite until observed. But wait, what counts as an observation? This is where the mystery deepens into something almost terrifying. Scientists decided to settle the question once and for all. They placed detectors at the slits themselves, devices that could record which slit each electron passed through. They ran the experiment again, now watching where each electron went, and the interference pattern vanished. The electrons behaved like ordinary particles, producing just two bands behind the two slits. Let that sink in. The mere act of measuring which path the electron took changed how it behaved. When we did not look, it acted like a wave going through both slits. When we looked, it acted like a particle going through only one. The electron seemed to know whether it was being watched. John Wheeler, one of the greatest physicists of the 20th century, pushed this strangeness even further with his delayed choice experiment. What if we decide whether to measure the path after the electron has already passed through the slits? We set up the experiment so that the choice to observe or not observe is made at the very last moment, after the electron should have already committed to its wave or particle behavior. Astonishingly, it still works. The electron's path seems to change based on our future choice. If we choose to measure the path, it will have gone through one slit. If we choose not to, it will have gone through both. The present measurement seems to reach backward in time, determining what the electron did in the past. Wheeler suggested that we are participants in bringing about something of the universe in the distant past. This raises perhaps the most important question in all of physics. What exactly is a measurement? What is so special about observation that it collapses the wave function? Is it the detector, the recording device, the computer that stores the data, or is it something else entirely? Some physicists have proposed that consciousness itself is the key ingredient, that the wave function only collapses when the result enters the mind of a conscious observer. This idea, championed by physicists like Eugene Wigner and John von Neumann, suggests that mind is not merely an accident of biology but a fundamental component of physical reality. The universe does not fully exist until a conscious being perceives it. This interpretation remains controversial, but no one has definitively ruled it out. Not everyone accepts the Copenhagen view. The many worlds interpretation, proposed by Hugh Everett, offers a different resolution. In this view, the wave function never collapses at all. Instead, every possible outcome occurs, but in separate branching universes. When the electron goes through the slits, the universe splits. In one branch, it went through the left slit, in another, the right. Both are equally real. We simply find ourselves in one branch, unaware of the others. This interpretation eliminates the measurement problem by eliminating measurement as a special process. But the cost is staggering. An infinite proliferation of parallel realities, constantly branching at every quantum event. Whether this is more or less strange than consciousness collapsing reality is a matter of philosophical taste. Perhaps the deepest implication of the double slit experiment is that we cannot separate the observer from the observed. Classical physics painted a picture of an objective universe existing independently of anyone looking at it. We were passive witnesses to a cosmic machine that ran according to fixed laws. Quantum mechanics destroyed this picture. At the most fundamental level, reality seems to require participation. The questions we ask, the experiments we design, the observations we make, all of these shape what we find. We are not outside the universe looking in, we are woven into its very fabric. John Wheeler called this the participatory universe. The universe, he said, is not a thing but a process, and observation is part of that process. So where does this leave us? A simple experiment with two slits has revealed that reality at its foundation is nothing like what we experience in daily life. Particles are waves until observed. The act of measurement changes outcomes. The past may not be fixed until the present observes it. And consciousness itself might play a role we are only beginning to understand. These are not mystical speculations. They are the implications of our best physical theories, confirmed by countless experiments over a century. We have pulled back the curtain on reality and found something far stranger than we imagined. This is just the beginning. In future episodes, we will dive deeper into consciousness, time, and the nature of existence itself. Until then, remember, in a universe where observation shapes reality, what you pay attention to matters more than you know. Keep observant.